This section is about using coordinates in graphics, so it's mostly about controlling the locations and sizes of things in graphical images. As an example of a simple graphic, here is a result from listplot. In a two-dimensional plot like this, the horizontal and vertical position of each point is specified by a pair of coordinates, one coordinate for the horizontal position and one coordinate for the vertical position. The list of numbers in this input, however, gives only the vertical positions of the points. When the input to listplot is a list of numbers, the horizontal positions are chosen automatically, using 1 as the horizontal position of the first point, 2 as the horizontal position of the second point, and so on up to however many points there are in the list. To use something other than 1, 2, 3, 4, and so on for the horizontal coordinates, the plot can instead be made from a list of pairs that gives both coordinates. This input, for example, uses list line plot to make a line connecting a sequence of points. The input to list line plot in this example is a list of pairs, giving both the horizontal and vertical positions of the points. Following a standard convention in mathematics, the pairs are called xy coordinates, where x represents the horizontal position of each point and y represents the vertical position of each point. By giving both the x and y coordinates in the input, the points can be anywhere and in any order. The coordinates can, for example, simply be random numbers. This input uses table and random integer to generate a sequence of random xy coordinates. A random sequence like that can also be generated by specifying the number of coordinates in the second argument of the random integer function. This uses random integer and listplot to make a plot of 100 points with random coordinates. Coordinate pairs are also used for specifying the positions of other things in two-dimensional graphics. For example, this draws a circle at a default location, and this draws 3 circles at different locations using the first argument in circle to give the coordinates of the center of each circle. This adds color styles to that input to make it easier to see which circle is which. This makes a graphic of 100 randomly placed circles, each with center coordinates up to 50. This uses table to make an array of circles with the locations of the circles chosen so that the circles just touch each other. The first argument in circle gives the position of the center of the circle, and a second argument can be included to give the radius of the circle. For example, this uses the second argument in circle to specify different radii for each of the 3 circles. If the second argument is omitted, the circles are drawn with a radius of 1. This makes 10 concentric circles by making a table of circles with different radii, all centered at coordinates 0, 0. This makes a sequence of circles with larger and larger radii and with the centers shifted progressively to the right. This draws 100 circles at random positions and with random radii. Coordinates are used in much the same way for other graphical elements, such as for points and lines and polygons. This input, for example, draws 2 polygons using the regular polygon function. The first argument in regular polygon gives the location of the polygon, the second argument gives the size of the polygon, and the third argument gives the number of sides of the polygon. So this input draws 1 regular polygon at location 1, 1 with size 1 and with 5 sides, which makes a pentagon, and a second regular polygon at location 3, 1 with size 0.5 and with 7 sides, which makes a polygon called a heptagon. This makes a graphic that combines a circle, a disk, and 2 regular polygons. The locations and sizes of these graphical elements are all given in similar ways. The first argument in disk, for example, specifies that the center of the disk is at position 2, 2, and the second argument specifies that the disk should have a radius of 0.5. Functions like disk, circle, and regular polygon are called graphics primitives. 2 other important graphics primitives are point and line. For example, this makes a graphic consisting of 3 points. The argument in point is a pair of coordinates that give the location of the point. The point graphics primitive can also be used like this, where the first argument is a list of pairs giving coordinates of several points. This shows the line graphics primitive used to draw a line connecting 3 points. The argument in line is a list of xy pairs that give the coordinates of points along the line. Another graphics primitive is polygon, which is used for specifying arbitrary polygons. For example, this shows polygon used to draw a triangle. The argument in polygon is a list of coordinates that give the locations of the corners of the polygon. Polygon can be used to draw arbitrary polygons. Regular polygon makes polygons where all of the sides and angles are the same, but since the coordinates of the corners in polygon can be anywhere, polygon can be used to draw polygons where the sides and angles are not all the same. This shows polygon used to draw a polygon with 20 corners at random coordinates. A polygon with random corners like this usually folds over on itself. Coordinates also come up in 3D graphics. This input, for example, uses Graphics 3D and the sphere graphics primitive to draw two spheres stacked on top of each other. The first argument in sphere gives the coordinates of the center of the sphere. In 3D graphics, instead of 2 coordinates, locations are specified by 3 coordinates, conventionally called x, y, and z. In the Wolfram language, x by default goes across the screen, y goes into the screen, and z goes up the screen. This makes a 3D array of spheres. The second argument in sphere gives the radius of the sphere. Radius 1/2 in this example makes the spheres just touch each other. Other graphics primitives like point and line can also be used in 3 dimensions. For example, this makes a 3D array of points. As in sphere, the locations of the points in 3 dimensions are specified by 3 coordinates. This draws 50 spheres at random positions with each coordinate going up to 10. One aspect of style that can be important in graphics is opacity, which controls whether it is possible to see through an object to see objects that are behind it. Opacity is specified using a style called opacity. Here is the previous input with opacity 0.5 included as a style for the spheres. Opacity 1 makes the spheres completely opaque, opacity 0 makes the spheres completely transparent, and opacity 0.5 draws the spheres as if they are partially transparent. If opacity is not specified, as in the previous example, the default is opacity 1, which gives spheres that are completely opaque. Here's a manipulate with sliders to show the effect of opacity and position on a graphic containing a sphere and another geometrical object called a dodecahedron. In this example, the variable x controls the coordinate x in the position of the dodecahedron. The slider for x changes the position of the dodecahedron relative to the sphere. The slider for the variable O controls the opacity of the dodecahedron between opacity 0.5 and opacity 1. Setting opacity to 1 makes the dodecahedron fully opaque, which blocks part of the sphere, and opacity of 0.5 makes the dodecahedron partially transparent. Manipulate is useful in many examples like this for showing the effects of styles and coordinates and other parameters in both 2D and 3D graphics. That's the end of the examples for this section. To summarize, here is the programming vocabulary from this section. Some of these graphics primitives came up in earlier sections, but here they were used with coordinates and with arguments for controlling size and location. The examples also included the opacity style specification. You can find more information about graphics in the Wolfram language by opening the Wolfram Language and System Documentation Center, clicking the Visualization and Graphics button, and choosing Symbolic Graphics Language from the menu that pops up, which brings up this page, which includes links to more information on all of the graphics primitives in this section and on opacity. In the documentation, opacity is called a graphics directive. Here are the exercises from the end of this section. As an example, consider exercise 14.2. Make 10 concentric circles with random colors. The table function can be used to generate the circles. This input uses table to make a list of 10 circles, all centered at the coordinates 0, 0, and with increasing radii. Enclosing that input in graphics draws the image. The circles can be styled with random colors using style and random color. Style can be added by modifying that input to style the circles in random colors.